Alright guys, my name is Favor and welcome to my YouTube channel, Dr. Ray School. Please, if you like my videos, do well to click that button, subscribe, like my channel so that I will drop more videos and you get more videos from my channel. So today we'll be looking at organic chemistry and we'll be discussing alkanes and alkynes. What is organic chemistry? Organic chemistry is a study of the chemistry of organic compounds, or rather of carbon compounds, with a few exceptions like the oxides of carbon, metallic carbides, and its triazocarbonate 4. So these three I just mentioned, they are studied under inorganic chemistry. So carbon is imperative, like it's important in the study of organic chemistry. So it is important we look at some of its features or properties. One of them is its ability to catenate. So carbon has the exceptional ability to undergo catenation reaction. By this, we mean that carbon is able to combine with itself to form straight, branched, and even compounds that are having a ring structure. So, another property of carbon is that it is a tetravalent element. Carbon is tetravalent. Why is it tetravalent? Is that from its configuration, it has K2L4. So it has 4 valence electrons. Hence it is tetravalent. It is in period 2 and in group 4 of the periodic table. Carbon is a non-metal. So looking at organic chemistry, or rather organic compounds, they all have some general properties. So generally, organic compounds are covalent in nature. And so being covalent, they will exhibit the properties of covalent compounds. What are these properties? One is that they all have low boiling point and low melting point. And this is because of the fact that they have weak intermolecular forces of attraction. Number two, they have non-electrolytes. Then three is that they are non-soluble in water, they are non-polar. There are some few ones that are polar, like those that have the very highly negative compounds, or rather groups, like chlorine and hydroxy groups. So these are polar. For example, alcohol is polar because it has the hydroxy functional group. Alright? So ethanol and the rest are polar. Then another example for another property is that they are thermally unstable, easily decomposed by heating or broken down by heating. What's the reason? Because they have weak forces of attraction between the adjacent molecules. The last one here, we'll be looking at their flammability and their reactivity. In terms of their reactivity being compared to inorganic compounds, organic compounds are very slow in reaction. And in terms of stability to heat, they are thermally unstable, decomposing to form products, and they burn exothermically. So that is the general properties of organic compounds. Now let's see. Initially we discussed that hydrocarbons could be aliphatic and aromatic. Then we went on to look at the fact that there is an ideal petrol, and that petrol should not cause knocking. So usually how they treat petrol not to cause knocking is that they add a petrol additive. There's a petrol additive called lead tetraethyl or tetraethyl lead. So tetraethyl lead is an important petrol additive which is used as an anti-knock. So this is an anti-knock agent. Anti-knock. It prevents knocking of petrol. So tetraethyl lead prevents the knocking of petrol. So let's see homologous series. Homologous series. What is a homologous series? It's just a family of organic compounds, because organic compounds are so many, they are so bulky. So we cannot really study them one by one. So how we study organic compounds is that we study them by the family. We group them that this is a group, this is a group, and this is a group. So these groups are called a family, or they are the homologous series. Now, every particular member under a particular group are called homologs. Examples of such homologous series are alkane, and the homologs under alkane are the methane, ethane, propane, butane, pentane, and so on and so forth. So there are many homologous series. So by definition, we just said homologous series is a family of organic compounds that follows a regular structural pattern, and in which successive members differ by a CH2 group or a molecular mass of 14 grams. So how we got that 14 is by the fact that carbon is 12 in terms of the molecular mass and hydrogen is 1. But there are 2 atoms, so 1 times 2 gives us 2 plus 12, 14 grams. Let's see an example using alkane as a case study. So alkane, we have methane, CH4, we have ethane, C2H6, we have propane, C3H8. Now let's use this example. We can see that there is a pattern going on, a regular and a structural pattern, in such a way that the carbon are increasing progressively by 1 down in series or down the group, and the hydrogen are increasing progressively by 2. That now gives us the CH2 we talked about earlier. So every homologous series, this is a common observation. Now in the homologous series, there is also something important known as their general properties. So what is obtainable in every homologous series? That is the general properties of a homologous series. One is that they all have the same general molecular formula. They all have the same properties of homologous series. One is same molecular formula. For example, all the alkanes, so under here, all the alkanes, the formula is CnH2n plus 2. All the alkenes, CnH2n. All the alkynes, CnH2n minus 2. All the alkanols, CnH2n plus 1OH. There are also other series, but we just discuss we just highlight the little ones, the few ones we have here. So that's one. Then two, they have same general method of preparation. Same general method of preparation. The way I will prepare methane is how ethane or propane is also going to be prepared. So they all have the same general method of preparation. They also have the same functional group. For instance, all the alkanes, their functional group is single bond. All the alkenes, double bond. All the alkynes, triple bond. And the alkanols, they have an OH functional group. The next is that they also have, because they have the same functional group, and the functional group determines the chemical properties of a compound. Hence, they will all have the same chemical properties. The other one is that they will also have the same physical properties. Then, so this is generally the property of homologous series. Before we now look into the different homologous series that we have, let's divide organic compounds based on their degree of saturation. So there are some groups we should also look first. We have what is called the alkyl group, and we have the functional group. These are the two groups that every organic compound should have. The alkyl group, they are like a derivative of the alkanes. You know that the alkane is what? Their formula is CnH2n plus 2. The alkyl is CnH2n plus 1. Now you can see that there's 2 here and there's 1 here, meaning that something is lost. So alkyls are derivatives of the alkanes by a loss of 1 hydrogen atom. So if alkane, for example, now let's say methane is CH4 methyl will be CH3, showing us that there is a short of a hydrogen atom in the alkyl groups. So what is the function of alkyl groups? Is that they help us to know the physical properties of organic compounds. Then the reactions that the alkyl groups can undergo is a substitution reaction. That is the reaction that they can undergo. Substitution reaction is very common to them. Substitution reaction. I'm also speaking alkyl. That is okay. They tell us the function, the physical properties. Then on the functional group is talking about an atom or a group of atoms, a bond. So by bond we mean it could be single bond, double bond, or triple bond. So if it's a single bond, is the alkane, double alkane, triple alkyne. So functional groups are simply bonds or a bond, an atom, a radical, or a group like the OH group, the COOH group, OH alkanol, COOH carboxylic acid. Then we have the CHO aldehydes or alkanates. So by definition, they are group of atoms, bonds, or groups that are peculiar to a particular compound, and they determine the chemical properties. So by comparison, these ones determine physical properties, these determine chemical properties. And every compound that shares the same functional group will also share the same chemical property. Take note of that. So let's divide organic compounds based on their degree of saturatedness into the two broad classifications. So it could be, we could have saturated compounds and we could have unsaturated compounds. By saturated compound, what do we mean? It means that these are compounds that have a single covalent bond. Meanwhile, unsaturated compounds, they have multiple covalent bond. Now, this multiple covalent bond could either be double or triple. Double is for the alkane, triple is for the alkynes. Alright? So, that is in terms of the bond. Then number two is in terms of reactivity. Saturated compounds are slow. They have slow reactions. While unsaturated, they are rapid in reaction, very fast, rapid reactions. Hence, alkane is more reactive than alkanes, and even alkynes are more reactive than the alkanes. But within this unsaturated group, where we have the alkanes and alkynes are more reactive than the alkenes. Why? Because they have a higher degree of unsaturatedness. So that is the reason why they are more reactive. Then a very distinguishing reaction for the saturated compounds is substitution reaction. It's a type of a reaction where a particular group is being replaced by an incoming group. But for the unsaturated compounds, they undergo addition reaction as opposed to substitution reaction that occurs for the saturated compounds. So this is addition reaction. Then still under addition reaction, the addition reaction is a type of reaction that the end result is to form a saturated compound. So if alkanes undergo addition reaction, let's say for example, alkane undergoes addition reaction with hydrogen, it will break down this double bond. One bond will be removed, so it will now become saturated. That's why it is following a stepwise, it's a one-step reaction. But for the alkynes, if they undergo the first addition reaction with hydrogen, it will break off one covalent bond. They are still left with two covalent bonds. It will undergo another kind of addition reaction with hydrogen to again break off the other hydrogen, the other single bond, to now form one bond remaining, which is a saturated compound. So what I'm saying in essence is that addition reaction is aimed at one, forming a less unsaturated compound, or two, forming a completely saturated compound. So if alkene undergoes addition reaction with hydrogen, it will form a saturated compound. But if alkynes undergo addition reaction with hydrogen, it will first form a less unsaturated compound, such as alkene, before on subsequent reactions, it will now form a saturated compound. So this is a dissociation factor. Then the last one here also is the fact that saturated compounds will not decolorize, so not decolorize one, bromine water. Then two, they will not decolorize. Okay, for here, they decolorize bromine water. Two, they do not decolorize acidified KMNO4, which is potassium tetraoxomanganate 7. But here they do decolorize it. So acidified KMNO4. So this is a clear. So if we are doing a qualitative analytic test, it will be observed that if a compound X on reaction with bromine water, there is no reaction. So we should suspect what? Saturated compound, and most likely alkanes. Or does not decolorize acidified KMNO4, the same alkanes. But if it decolorises alkane, either the bromine water or this acidified product compound, then it is an unsaturated compound, which could either be the alkanes or the alkynes. So this is the difference that exists between saturated and unsaturated organic compounds. Now let's look at the three homologues of today's discussion. The first being alkanes. Alkanes, also known as paraffins. In other words, they are paraffins. They are oil formers. Okay? So general property of the paraffins is that they burn with a pale, non-smoky, non-luminous flame. That is their general property. And they undergo substitution reaction because they are saturated. The first homologue, which is the most important member, is when N equals to 1. That is methane. Methane, also called marsh gas, because of its destructive distillation process. Marsh gas. Okay, that is the other name, and the formula is CH4. Marsh gas. So normally all the alkanes from N equal to 1 to N equals to 4 or 5, they are gases. So methane to pentane are gases. Hexane to decane, these are liquids. But from 11 upwards, all the icosane, undecane, dodecane, these are all wax or solid in nature. All right. And also, it also follows that, you know, if we are moving from gaseous states, gas to liquid, then to solid, you will agree with me that there is, so if we are going in this order, from solid to liquid to gas, solid we have lowest kinetic energy, intermediate and highest. Also, solids we have highest boiling points. They do not boil easily, and highest melting point. So, if I should give you, let's say, methane gas and hexane, it is to be expected that first, methane is N equals 1, hexane is N equals 6. I said from 6 up to 10, they are liquids. So hexane now, we have a higher boiling point and higher melting point than the methane. Or methane, we have a lower melting and boiling point than hexane. So methane gas. What are some peculiar features about methane gas? Is that it is in its structure, it is sp3 hybridized. Very important. Hybridized. Okay? This sp3 hybridized. It is tetragonal in shape. A bonding angle of 109 degrees. And then, okay, so these are some of the peculiar things about methane. sp3, tetragonal, and a bonding angle of 109 degrees. How do we prepare methane in the laboratory? Methane gas is prepared by the action of reacting sodium ethanoate with an alkali, preferably soda lime. In this reaction, we have sodium ethanoate with an alkali. This is an alkali. Alkalis are just usually soluble bases. So this alkali now, usually there are two things it could use: caustic soda or soda lime. But we usually use this, not this. Okay? This, not this. Why do we use this? Because this is not deliquescent. And two, it does not wet glass. That's the reason why we use it. So, on reacting the alkali with the sodium ethanoate, we will form sodium triiodocarbonate 4 and give off the gas we are producing. So this is how methane gas can be formed. And the gas is usually collected over water. It is collected over water. The reason being that it is lighter than air. Now remember we said all particular series have the same general method of preparation. So the way I prepared methane is also how every other member of the alkane series is going to be prepared. So we have to prepare C2H6, C3H8, that is ethane propane. It's just to increase in factor here. So it becomes C2H5 COONA plus Na2CNaOH, giving us Na2CO3, sodium tricarbonate 4. Then here is just 3H7COONA, sodium propanoate, sodium butanoate, plus an alkali here, giving us sodium triiodocarbonate 4. So, what we are simply saying, remember we said that they have the same method of preparation. You can say they are all the same. The only difference is that I increase the ethanoate by increasing it gradually as we go on. Alright, so in the exam, you might be told that how could pentane be produced? It is produced by now using what? Since we got methane from sodium ethanoate, ethane, sodium propanoate, propane, sodium butanoate, pentane will now be sodium hexanoate. What I mean is that we got methane, which is N equals to 1, from ethane, that is N equals to 2. We got ethane, N equals to 2 from N equals to 3. In other words, we will get pentane, which is N equals to 5, from sodium hexanoate, N equals to 6. The gas, after you collected the gas, the cylinder must be withdrawn on time to prevent withdrawal or sucking back of what is formed. So let's see the physical properties of methane. Physical properties of methane. Methane is a colorless, odorless gas. Methane is neutral to litmus, that is 2. Methane is less dense than air, that is 3. And then methane gas, we've already looked at. Okay, so these are basically, they are neutral to litmus. They have no action on litmus paper. So these are the physical properties of methane. Then the chemical properties of methane. 1. Chemical properties. One, which we must not forget, is that it undergoes substitution reaction, which is the hallmark of all saturated compounds. And by substitution reaction, it can react with hydrogen or with halogen. So the one that it reacts with hydrogen is called hydrogenation reaction. That with halogen is called halogenation reaction. There are different halogens. Halogen are the preserved element. We have chlorine, bromine, iodine. So the one that it reacts with iodine is iodination, chlorine, chlorination, bromine, bromination. So this is the type of substitution reaction that the methane gas can undergo. So let us discuss hydrogenation reaction. So for the substitution reaction, the key one here is halogenation reaction. Basically, halogenation reaction, which will be chlorination, that is reacting with chlorine, bromination, reacting with bromine, and then the iodination. So this is basically what we're discussing now, not hydrogenation. Okay? So basically, methane undergoes substitution reaction. If it undergoes that reaction with halogen like chlorine, is chlorination, bromination for bromine, and iodination for iodine. Let's now look at chlorination reaction. So this is methane gas. We have CH4, plus chlorine gas. What is to be gotten? In substitution reaction, this is how you write it. So we have CH4 plus chlorine gas. What will be formed? Okay. CH4 plus chlorine gas. In this reaction, as the attacking agent is coming in, one is going to be removed. So let's say chlorine comes in here, hydrogen will now replace chlorine, so that you will now have CH. Now this hydrogen has been removed and chlorine has taken its place. The hydrogen being removed will now go and take the place of chlorine to form HCl, hydrogen chloride. So in this case, we have CH3 and chlorine. CH3 chlorine plus HCl. This is called chloromethane. Chloromethane. Now you must not forget that I said that organic reactions are usually slow, hence they need catalyst. The catalyst used in this reaction is ultraviolet light, UV light. and this is the first product. So in the chlorination reaction of methane, the first chlorinated compound form or product form is chloromethane. Do not forget that. Secondly, because the chlorination reaction is a stepwise reaction, occurs in 4 steps or phases. This is phase 1. In phase 2, this chloromethane will further react with chlorine. So chloromethane reacts again with chlorine to form products. So how do we express it? We have C, this is now chlorine, H, plus chlorine. This chlorine will attack this, and this will replace. So we now have HCCl, Cl. So this H has been removed, and chlorine has taken its place. And H. The H being removed will now come and combine with chlorine here to form HCl. So we have CH2Cl2, CH2Cl2 plus HCl. So this process continues again, and we now have CH2Cl2 going for another round of reaction to now form CHCl3 plus HCl. Okay, this second one is called dichloromethane. Dichloromethane. Then this dichloromethane is now what is undergoing the third reaction with chlorine gas to form CHCl3, giving us HCl. So this is called trichloromethane, otherwise called chloroform. So chloroform will undergo the last reaction, giving us, so chloroform is CHCl3 plus Cl gas, give us, so this time around we have CCl4 plus HCl. This is called tetrachlorocarbide. Tetrachlorocarbide or tetrachloromethane. So the last product form is tetrachloromethane, and UV light is always used, and it's a 4-step reaction. Let's see the uses of methane. Methane is used, so the trichloromethane is used as an analgesic in hospital to reduce pain during surgical processes, which is also known as chloroform. While the tetrachloromethane is an important agent, a dry cleaning agent in laundry. So it is an important dry cleaning agent in laundry. So let's see how we can name some few alkanes. But before we discuss the nomenclature of some few alkanes, let's see the concept of isomerism in alkanes. So isomerism basically means iso means the same. So these are compounds that have the same. So there are different types actually, but I'm going to be narrowing my teaching to structural isomerism. So they have the same molecular formula, but they have different structural formula or different structural arrangements. And it is to be expected that since they have the same molecular formula, they will have the same chemical properties, but different physical properties. So structural isomers have the same molecular chemical formula, but different the same chemical properties, but different physical properties. We take for the alkanes now, we have butane. So butane has two structural isomers. So this is butane, CH4N, C4H, C and H4, like C4H10, okay? I use these things to represent the hydrogen atoms. This is actually called normal butane or N-butane. Now, to get the other form of butane, it's just removing this from here and forming something like this. So this is called isobutane. Isobutane. Or, so later on I will teach you people how to name compounds. So let me just, this is called 3-methylpropane. So 3-methylpropane. 3-methylpropane is the same thing as, rather 2-methyl. 2-methyl. The same thing as isobutane, meaning that it's an isomer of butane. How do you have 2-methyl? You count 1, 2, 3. At carbon 2, we have a methyl group, so 2-methylpropane. So let's see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here is also 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also 10. Now, when you have isomers such as these two, this has a branching point. This is just straight, no branching point. The more an isomer that has no branching point has a higher boiling point than the one that has a branching point, which means branching decreases the boiling point of isomers. The more they are branched, the lesser their boiling point. So if there are two isomers, there are two branched isomers. If one only has one branching point, the other has two branching points. The one that has two branching points will have the less or the least boiling point. All right. So butane has two structural isomers, which I've just shown, N-butane and then the isobutane, N-butane or isobutane. Then we have what? Pentane. 3. So pentane has 3 structural isomers. We have 1, 2, 3, 4, 5. This N-pentane, that is normal pentane. So we could also form 1, 2, 3, 4, and put the last one here. This is now called 2-methylbutane. 2-methylbutane. So 2-methylbutane. And the third one, or the last one, is 2,2-dimethylpropane. So these are the different structural isomers of pentane. And the last one here we will discuss is hexane. Okay, it has 5 structural isomers. So let's now look at the alkenes. They are also called olefins. Alkenes also called olefins. The first member is ethene. So ethene, it is sp2 hybridized. sp2 hybridized. It is triagonal and an angle of 120 degrees. So they are, unlike alkenes that have sp3, tetragonal and 109 degrees. How can they be prepared? Ethene is prepared by dehydration reaction. So you dehydrate ethanol dehydrate ethanol using excess concentrated sulfuric acid H2SO4 at a temperature of 180 degrees Celsius or 170 degrees Celsius. So the reaction involves removal of water molecule. It will now form a tin. So this is generally how it can be formed using the catalyst. Using the catalyst H2SO4 at 180 degrees Celsius. So, in this reaction, the ratio of the acid to the alkanol is 2:1, which means this acid is used in excess of this ethanol. We can also produce ethene by the cracking of hydrocarbons. Okay, it's another method through which we can produce ethene. Physical properties are almost similar to methane, just that it has almost like a faint sweet smell. They are less soluble, they are insoluble, low, less dense than air, and they are neutral to lithium. But for their chemical properties, unlike methane that undergoes substitution reaction, these ones undergo addition reaction, which is a hallmark of every saturated compound. So in their addition reactions, we have C2H4 combining with hydrogen gas. It will form C2H6, and the catalyst used is nickel granules or platinum. So we use nickel or platinum. This reaction is called hydrogenation reaction. So in the hydrogenation of alkenes, nickel or platinum is used. And it is important in the hardening of oil. Hardening of oil. A reaction also catalyzed by nickel, forming fat known as margarine. So this is an important reaction of the alkenes, particularly ethene. And it is an example of an addition reaction in which the alkene that is unsaturated is made saturated, which is forming the alkene. One important feature of alkene, like ethene, is that it is stored under propanone or acetone. So in the storage, it's stored under propanone or acetone cylinders. So another chemical property of the alkenes is that they decolorize bromine water, and they also decolorize acidified potassium tetraoxomanganate 7. So let's see how these form isomers. So they undergo a type of isomerism called geometric isomerism. So particularly we have it in this way. So we have hydrogen. Then we also have another example, such as we have CH3, and hydrogen here. For geometric isomers, they could be cis configuration or trans configuration. Cis means same, trans means opposite. So if these groups are on the same side, it is cis configuration. If they are on opposite side, it is called trans configuration. So this is named by counting first the carbon atoms. 1, 2, 3, 4 is good. Then at number 2, 1, 2, there's an in, a double covalent bond. And the groups are on the same side. So it is 6 butene, 2 in. While here on opposite side is trans butene, 2 in. The reason why we have geometric isomerism is because there's a restriction of the rotation of these two carbon atoms. Why? They are held in space by this double bond. We could also have, so this is for alkenes, all right? We could also have a state whereby we have carbon bonded to chlorine on the same side, and hydrogen here. And then chlorine on adjacent or opposite side. So in this case, we can't, there are just 2 carbons and 2 carbons, so it is 8. Then the chlorine here, the chlorine are on the same side, so it is 6. Chlorine is on carbon 1 and on carbon 2, so 6, 8, 6, 1, 2, dichloroethene. Okay, 1, 2, dichloroethene. Why here is trans because the chlorine are on opposite side. And chlorine is on 1 and on 2 carbons. So trans 1, 2 dichloroethene. Still speaking on isomerism, there's another type of isomerism known as optical isomerism. Optical isomerism, which occurs in compounds that have a chiral center. So a chiral center simply means this is carbon, this is a chiral carbon now, that is bonded to OH, or let's say carbon bonded to, let's say here is X, 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 X. These are 4 groups bonded to carbon, and they are the same. While here we have carbon bonded to X, 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 Y. So in this case, let me call it A, and this is B. Carbon A is a chiral center for a chiral carbon because there are 4 the same groups attached to it. But carbon B is not a chiral carbon because the 4 groups are not the same. So for an object to have optical isomerism, there must be at least 1 chiral center, which will make that compound to be able to rotate this plane of polarized light either to the left or to the right. When it does it to the right, they are called dextro-rotatory, or D, or plus. To the left, they are called levo-rotatory, L or minus. So examples of compounds that have optical isomerism are glucose and lactose. So at the alkenes, then now look at the alkynes, which is the last one. They are called acetylene. Acetylene, that's the alkynes. They are also unsaturated. The key member there is ethene rather, with the formula of C2H2. So they have the triple covalent bond. So what are their features? They are sp hybridized. Unlike alkenes that are sp2, they are linear in structure with an angle of 180 degrees. How do you prepare them? They are prepared by the action, so laboratory preparation. Preparation is by the action of cold water on calcium dicarbide. So we get C2H2, and we have water formed. So the action of cold water on calcium dicarbide will form ethene. So that is basically how the ethene can be produced. So their properties, they are also less dense than air, neutral to litmus. But for chemical, that's the physical properties. For their chemical properties, they are also almost the same as the alkenes. So just like the alkenes could react with hydrogen, a reaction called hydrogenation reaction. The alkynes, so here this is C2H2. If alkyne, if ethyne undergoes hydrogenation reaction, it will form ethene. Then further reaction will now form ethane. So, and it's also catalyzed by nickel or platinum. So that is basically their reaction. Then in terms of combustion reaction, both alkane, alkyne undergo combustion reaction if there is excess air to form carbon 4 other than water. Heat is involved, so it is exothermic. But if there is limited air, carbon 2 oxide and water, because air is limited, that is oxygen supply is cut short, or is made not abundant. Okay, so what are the uses, particularly for the alkenes? Uses of the alkenes. Now, there's a concept called polymerization reaction. It's a reaction whereby a simple compound condenses adds to form a larger compound. Okay, they are called polymers. So alkenes could form polymers like polystyrenes. Then another important one is that they are used in agriculture. Ethene so ethene is used to hasten, that is to speed up the ripening of fruits or agricultural products. So that is what ethene is used for in the agricultural setting. It could also be used to form polyvinyl chloride. Polyvinyl chloride. That is another important use of the ethene. So let's look at the tests for these compounds. So we have alkanes. This test is like a summary also. We have the alkenes and we have the alkynes. So here examples. Alkene, we have ethane. Here we have ethene, ethyne. Then common reaction for alkane is substitution. They cannot undergo addition reaction. But for these two, they can undergo addition reaction. Then here, bonds or functional group or the bond. Here is single covalent bond, double covalent bond, triple covalent bond. Then saturation. These ones, they are saturated. These are unsaturated. These are also unsaturated. So hybridization, sp3, sp2, sp1 or sp. The angle 109, 120, 180. The shape tetragonal, triagonal, linear. Then the reaction with bromine water. Here, no reaction. Here, decolorize. Here, decolorize. Reaction with acidified potassium tetraoxymanganate 7, no reaction. Decolorizes and also decolorizes it. But how can we now distinguish alkynes from alkenes, since both are almost the same in terms of reaction with bromine water and acidified potassium tetra or sulfate, tetra or matter 7. So the way we distinguish them is by using silver nitrates. So using silver nitrates, these ones show no reaction. Alkene show no reaction, but alkyne will decolorize silver nitrate. This is a distinguishing test that distinguishes the alkynes from the alkene.